Let's get started. So yeah, it's my great pleasure to welcome Deepak Pathak for a CAIDA seminar today. Just a little bit about him. So he completed his PhD at UC Berkeley, advised by Alyosha Efras and Trevor Darrell. He then did a postdoc at UC Berkeley with Peter Abil. And currently he's an assistant professor at CMU in computer science, and he's also a member of the Robotics Institute at CMU. He's spent time at Facebook AI Research, Microsoft Research, and has also co-founded a company, Visage Map. He's a recipient, he has, among other accolades, he's the recipient of faculty awards from Google and Sony. Yeah, and his work has been featured fairly widely in the popular press, including Wall Street Journal, Economist, Quanta Magazine, Wired, etc. And yeah, and so he's really done a large variety of interesting work, much of it at the intersection of reinforcement learning, computer vision, and robotics. And so he's made great progress on representation learning, particularly via self-supervised methods, which nicely spans all those areas. So it's a great pleasure to welcome Deepak here today, and I very much look forward to his talk. Among other things, it has robots that learn how to walk. So what's not to like? And last comment is that I'm happy to monitor the chat for questions that come up. Welcome, Deepak, and take it away.
Okay, thank you so much for the kind introduction, and it is my pleasure to be giving a talk here. And I wish it could be in person, but let's enjoy. So I try to compensate for not being in person by showing some cute and cool videos. Okay, so let's start. And today I'll talk about robot learning in general, and in particular, building how to build robots that can adapt rapidly to function in diverse tasks and environments. But before we go into how to adapt, let's recall what is the goal of robot learning. And our long-term goal is basically to build agents that can display this general purpose embodied intelligence. But what does that mean? So consider an example here of the robot below. When introduced to a new environment, this robot should be able to achieve all the tasks that the user gives to it. For instance, you may ask it to cook, to shop, or I don't know, to fix things. In other words, what it really means in concrete terms is that we want the robots to be able to achieve thousands of tasks in thousands of environments. But unfortunately, this grand goal is very far from where things are today. And like most of the successful results in robot learning today are focused on in solving one task in one environment. And it is extremely difficult to generalize from one scenario to other, like playing Go to grasping objects. And this generalization problem is not just an issue in robot learning, for instance. This has been a problem which is pervasive in all forms of learning, especially deep learning, I would say. And let me try to show you an example to prove that. So let's consider the most simplest and the most well-studied problem, that is of supervised learning. Okay, here we have the case of image classification, where the goal is that given an input image, you want to learn a model to classify it. In this case, it's Labrador. The way we train this model is by showing it lots of images of dogs, like one more image, one more image, one more image. And these images come from a large data set, which is split randomly into training and test, right? And here is a result which we are all very proud of. This glorious result displaying the success of deep learning, which is like achieving superhuman accuracy on this ImageNet test set. But let us see how well do these models transfer to new scenarios. So I take this ResNet 50 model and I test it not too far on images of dog, but from a video in YouTube. And what happens? Well, this superhuman model ends up finding things like cobra snake, prey fish, flatworm, and the accuracy drops from this glorious 80% to merely 20 to 25%, which is very low in these examples, and it is finding very wrong outputs. But if you discuss this problem with a computer vision person, the answer would be not very surprising, because this is kind of what we expect. Like, the reason it does not generalize is because the images in ImageNet are taken by photographers with dog at the center, good lighting, frontal pose, and all that. All of these conditions are rarely true in the videos. But to me personally, this highlights a major issue in the way we approach learning today. And the learning paradigm, the way we approach today, is we start with this assumption, like, which you can find in any machine learning book, like maybe in the first page of the book, is like things like that this data at your training time and the data at your test time, we just assume that it comes from same distribution. But in reality, this is not true. And whenever this assumption gets violated, our models fail to generalize. And this problem is more apparent and a bigger one in robotics. In this, like, to extending the same analogy to control, here we have a robot that can do lots of parlor tricks, but apparently fails to generalize to a simpler task of just putting a box on the table. And the failures in robotics are more catastrophic and can cost you thousands of dollars, unlike classifying a wrong image in ImageNet. So what I believe the major problem is not getting something to train, but it is to basically generalize beyond training and to have them function in the real world. And in today's talk, I would like to argue that probably the only scalable solution to this problem is to keep adapting all the time in a lifelong manner. Just keep adapting, as is the case in biological agents. So what we want to do is you want to go from this current paradigm of training and freezing weights and testing, and then just hoping that the things will work at test time. What we want to do is build systems that can adapt rapidly and continually. And today's talk, I'll talk about some approaches that can go from this paradigm to this continual adaptation paradigm. And this basically boils down to this question: how do you computationalize the idea of adaptation in a way that is scalable and practical? Okay. So for the purpose of today's talk, let us break down our original goal of solving thousands of tasks in thousands of environments into two concrete subproblems. And the first subproblem that we will study is, how do we build agents that can function within the same task, but generalize to diverse environments, lots and lots of environments. The second problem is focusing on same environment, but generalizing to diverse tasks. And as you can imagine, this is like a very natural separation. And if we want the robots to be general purpose and embodied, we want both of these things. But breaking down this whole goal into two subproblems help us study them in a more scientific manner and build algorithms at the first place. So to study the first subproblems, I'll focus on robots that can actually go to diverse environment and not static at one place. So like walking robots or navigating robots. Second problem, since it's same environment and diverse tasks, this is a problem which is more suitable for manipulation, like at least in today's time frame, with robotic arms that are usually fixed to a table and do things in there. So we'll study problem or the approaches in both of these subproblems today. So let me begin the talk by talking about this first subproblem, which is focusing on same task but diverse environment. So just to make things very concrete, let's say our problem setup here is that we train the robot in one scenario, and the robot task is to walk forward or run forward. And the goal or the evaluation which we want this robot to excel on is adapting to diverse environments. Okay. In particular, I'll talk about our recent work in this direction, which we call rapid modal adaptation for legged robots. And instead of talking at a very high level, I want to go in depth of these approaches. And if there are any questions in between, I would love to take questions. So before I go into the approach of how does RMA work and what is it what kind of adaptation is it doing, let me first motivate the idea by showing some results in between. So what I'll show you next are a set of results where the same policy which we trained in simulation was deployed in the real world, and the robot is adapting in real time to the new scenarios. And note that this policy was only trained in simulation, and all the environments that we are showing in the videos coming in a second, the robot has never seen those environments before. So it is a generalization result, which I would like to emphasize throughout the talk. Okay. And the robot is blind, so and it is walking from proprioception, from its own sensing, not of the environment. So here is an end result where we introduce the robot. Can you hear the volume? Just to check. Can someone confirm if they can hear the volume?
Yes, we can.
Okay. I was asking because I put the earphone on. So here we see the robot walking on the rocky terrain next to the river. And as you saw here, the robot actually was able to avoid obstacles by incrementally moving leg upwards and until it avoids the rock. And I'll come to this more in the result section. Here is one more example of a robot going down the stairs. Note that this robot was never trained on stairs. And this is a test time result where we introduced the robot to the stairs for the first time. Now, as I said in the beginning, the robot is blind, but even if the robot was not blind, it would, even if the robot could see and was not blind, it would still need to adapt to things which are not perceivable. Like if we see this example, the robot has to avoid this dip. So in this patch, there's a certain dip. And the only way to avoid falling from the dip is to be reactive from your own sensor input. And vision would not have helped here. Okay, one more example of robot trying to walk over vegetation. One more example where the robot is trying to walk over unstable ground. And you can see this is a construction site and the legs of the robot are very thin. So as it moves, the ground kind of deforms. So it's difficult to adapt in this scenario. Here is one more example where it's walking on a wet mud and the mud sinks into the ground as you put your feet into it. So you have to reactively adapt at a very high frequency to such changes. And here is sand. Now, sand is not very hard for humans because we have a very large surface area on the feet, but this robot has a very low surface area. So sand is also acting as a deformable ground. And finally, to emphasize the point that all the results that we saw so far are from a single policy that was deployed without any modification or tuning directly in the real world. And one funny part here is that in this project, we spent a lot of time in testing. So this whole testing was done during the pandemic and spread over like 2 months in the real world. Okay, so now let us see what is the key idea behind this approach. And the approach is super simple and straightforward. And the adaptation part is the main interesting portion here. So I'll quickly describe the approach and then we can go to the analysis of the approach. And I can take any questions in between again. So how does it work? Well, you would like the robot to walk as well as possible. And as I said earlier, the robot is trained completely in simulation. Okay. So in simulation, we want the robot to take the current state and its last action or whatever, and output the next action that it should take to move forward. Now, the way we train this robot is so that it can work really well. So we feed it the ground truth information of the ground. So we feed it the mass, center of mass, friction, terrain height, and motor strength, and all those information. And we feed that via network, which encodes all this environmental information and pass it to this base policy. Okay. Now, in training time, since we want the robot to be robust, we generalize or we randomize all these parameters very heavily. But note that, so this is very common in something called domain randomization in robotics or in robot learning. But this approach, note that is kind of opposite of randomization. So you are randomizing all the terrain and every information, but you are not asking the robot to be invariant to those changes. You are actually conditioning on them. Okay. So we are not training a single generic policy that works well everywhere, but we are training a policy that is adaptive, which knows what it is dealing with. Okay. All right. So as we see in the figure, the environment parameters are compressed into this extrinsic vector Z, and which is then fed to the base policy. And we train this, so we call this extrinsic vector because this vector is encoding the information coming from outside the robot. So it's coming from the environment. The information that is coming from the top is intrinsic because that comes from the robot's own joints. So this extrinsic vector is being computed jointly with the policy. Okay. For some reason, okay. And we train this policy basically via reinforcement learning in simulation. And on the right, you can see the environment it is trained on. And this environment is the only environment we train this on. And we vary programmatically the height, the variation of all these terrain values randomly. Okay. Now, and you condition on those changes by this extrinsic vector to the base policy. Now, one important thing I would like to emphasize here is that we are not using any predefined leg swing motions, like how the leg should move and all that. The policy directly outputs the joint angles for the robot. And like so we are applying learning completely ground up. So without assuming any access to control stack or any such thing. So it's not like we're not using sine wave motions for the legs, etc. Okay. And finally, yep.
I wonder if I could ask a question.
Correct. Yeah, you can ask.
So you mentioned that you're learning this extrinsic vector. So do you set the size of that, and then the training process will figure out what those values mean? Okay.
Yes. So this is all reinforcement learning, and the gradients flow from the reward all the way to the base policy and also to the encoder. These are both networks.
And in terms of the parameters that you varied, how did you pick those? Was it just every parameter you had in your simulation environment, or were these selected somehow?
We didn't hand select them. It's like we have 42 parameters here in the input, and this is 8 dimension. So we did not choose, like, it's like whatever people do standard in the community, we just copied these parameters. So it may be a superset. It is in no way a subset. So we did not tune that much.
Okay, thank you.
Yeah, okay.
I'll just add a very quick follow-on question. So is there any memory in the encoder or the base policy? Because you could imagine to detect a foot slip or something, it's useful to look at a time window of the motion.
Correct. So there is no memory. So it's completely reactive at the current. The only memory here is that you can see this, it takes 80 minus 1. That's the only memory you have, but this is completely reactive.
Got it. Okay, cool.
But notice one thing, that there is this terrain height and motor strength. So it sees the next, the current distribution of the environment, but no other memory here. Okay. All right. Now, the question is, how can we deploy this? Well, there is an obvious problem that the extrinsics are unknown in the real world, because these values are not available for us in the real world scenarios. And so you can call this a sim to real gap, but the problem is slightly deeper than that, because these values, even if we could find them in the real world, they will not be constant for every environment. And even in the same environment, these values may change as to what is their effect on the robot. So how do we go and solve this problem? So what we do in this setup here is we try to estimate this information from some other signal. So in the training time, we learned this extrinsic vector from privileged data, like the environment parameters. But in the real world, we would like to estimate them in the runtime at real time. Okay. So our main insight is to estimate these extrinsic values from the history of the observations of the robot. Okay. Now, why is history good enough to estimate the extrinsics? And basically, the intuition here is that when you command a robot a certain set of actions, like you want to say, okay, move your leg in this manner. And when you actually measure what happened, like the actual state in your history, if there is a discrepancy between what you command and what really happened, that discrepancy usually is the result of the extrinsics. Like if it's sand, it will obey your commands differently. If it's rocky terrain, it will obey your commands differently. So history actually has the information about what is the effect of the extrinsics on the robot. So that's a reasonable thing to learn this from. Okay, so we build this adaptation module, which will estimate these extrinsics from the history of the robot. Now, then we can, once we have this module somehow, I'll discuss in a bit how to train that. But if we have that module, then we can continuously estimate these extrinsics online in the real world. Okay. So now the question is, how do we train this module? And the approach is super simple. So phase one, I described already. In the phase one, you train reinforcement learning completely end to end. You learn both the base policy as well as this encoder. And in the phase two, you keep base policy fixed. Okay, so the red boxes means they are trained. So in phase two, base policy is not trained, it is fixed and borrowed from the phase one. Then you only train the adaptation module, and you train this via supervised learning. So you try to collect data, and from that data, you go from history to the target, which is generated from the environment encoder. So this is basically supervised learning. Okay, I hope this is clear. So phase one, reinforcement learning. Phase two, supervised learning, done from the data collected on the robot. Now, finally, our method is ready for deployment. So we have this adaptation module and base policy. Okay. Now, the key part of this two-phase thing is we are able to run the base policy and adaptation module at different time frames, because base policy is completely reactive, as the question was asked in the beginning. Since it's completely reactive, it can run really fast on the robot, like 100 hertz or so, even with a deep network. And this adaptation module is slow because it is processing history and estimating these extrinsic vectors. This can run at a low speed. But in our system, these two are completely asynchronous. So they don't have to be synchronized. Like adaptation module can generate some extrinsic vector, and base policy uses the latest one from the module. It doesn't have to be aligned with the current one. The second benefit is that now you can run this adaptation module continuously. So even let's say the environment remains the same, like the sand, you don't just adapt and find this vector once in the beginning. Actually, you can keep finding this every second or every half a second. And the reason for that is that even though the environment may remain the same, like sand, but the effect of sand on the robot, that changes continuously, depending on what is the shape of the robot right now, or is it tilting, is it not tilting, is it straight? Like all these conditions affect the effect of the same environment. So we estimate these Z values continuously. Okay, so that's all about the approach. If there are any questions I can take now, otherwise let's move to more evaluation of this. And let's try to really ablate every point in this method.
Hi, Deepak. Jeff
Okay.
Flynn here. It's nice to see you.
Yeah, oh, hi, Jeff.
Would you mind going back, well, now 2 slides?
Yeah.
I think I missed the phase 2 learning technique. Can you say that again, please?
So phase 2 is basically supervised learning. Okay, so we copy the base policy from phase 1 into the phase 2, and then we collect data, and the data, whichever data we are collecting in the robot, in simulation also, we just regress from the history, and the target comes from the encoding of the environment parameters, which we have access to in simulation.
You're basically saying you have to infer from the Z vector what the, or sorry, from the observation stream, what the initial 48 parameters or whatever they were are.
So not the 48, the encoding of them. This is 48, but this is only 8 or 10. So very like in the feature space. So this
given
is
a cloned encoder of the 48 to the Z vector, you have to infer the correct Z vector for the observed environment over and over again from simulation. And then the hope is that that generalizes to the real world to produce an appropriate encoding of the ground truth properties of the world. Correct.
Now, this may seem magical, but there is one detail which I skipped here intentionally because it may be too detailed. But the question is, why will it generalize? So I can come back to this later as well. But this phase 2 actually is supervised learning. So you have much more power here. So this is very efficient in learning. And what we do is we actually collect data where the robot. So what we do, the question is, when you're performing this phase 2, where is the data coming from? Right? That's another question. Like you can perform regression, but is data coming from phase 1, or do you recollect the data? And in this case, we recollect the data. So what we do is we pass the estimated ZT, so Z hat T coming from adaptation module, and we pass that to the base policy, and we collect that data. So in the beginning, this module will be very bad because it has not learned yet. And when it is bad, the base policy will fall. So you also get data which is not only good, but also the one where it is bad or where this module is diverging. And when you get that data, you have a target for that data, which is from the true privileged information. And then you train this module on that data as well. So in a way, you are kind of doing active learning in the scenario. So you're not just hoping that from this data I'll generalize, you're collecting data where this module fails, and then you improve it over there.
Okay, thank you very much.
Yeah, okay. All right, so let's move to the results and let's see how well each of these things perform. So first, let's see just simple direct results of this approach in the real world. So earlier I showed you outdoor examples, but here are, again, it was pandemic. So it's a home created into a lab kind of scenario. This is Ashish's living room. And you can see the robot is able to, one example here is like the plank is moving with the robot forward. So this online adaptation is really helpful in these scenarios. One more, here is a mattress. So we put the robot on the bed and it can walk forward. I'll show more examples, longer examples below. But the key thing in this mattress is, in mattress, you don't get a force feedback on the legs. So because mattress depresses in the as you put feet over this. So this is really a hard task. So one more example here is this robot trying to walk over this terrain. So here is a plank and the surface is oily and you're throwing the weight on top. So I'll show each of these examples in more detail with respect to an analysis. But we did a very thorough investigation of this approach and it really works in diverse scenarios. Okay, so let us see here. So let us first compare this approach to A1's built-in controller. So far I was talking about all learning-based methods, but now we would like to compare this, how well this method works with a control-based baseline. Now, it is very common in the control-based methods to kind of assume a leg motion, that very sine wave-like motion like this, because the robot actually, the locomotion is very periodic thing. So you can actually parameterize it very well. So here is the comparison to the rope controller that comes with the robot. So on top, you have this robot, okay, it kind of falls when it's a sudden dip, and bottom is RMA. Okay, so it also encounters unstable foothold, but it is able to maintain its balance and move forward. Here is the opposite, like you have to go up, and note the robot is blind here. So that behavior that you saw, it actually learns to kind of move its leg up to avoid it, since it cannot see the obstacle. So it has learned this behavior using leg as a stick. And here is mattress. Now you may ask, okay, wait, why is it just jumping around? Because mattress gives you very erroneous feedback on the leg force sensor, which completely throws off any classical controller usually. And here is RMA. Now this was comparison to classical controllers, but let us see how critical is the adaptation piece to this, or is the base policy strong enough? So here, what I'll show is the top row is the method, which R method, and then bottom row is without adaptation. Now, what does that mean is we still adapt, but we only find the extrinsic vector once in the beginning and then keep it frozen. In the top, we estimate it continuously online. Okay, so let us see the testing. The testing here is it's not just walking, because walking is easy. Walking can be done without adaptation. So here we put 8 kg payload on the robot. Now 8 kg is really heavy. So if you try to walk with 8, so it's not 8 pounds, it's 8 kg, but so it's like really heavy. And robot itself is 12 kg. So it's, and we did not have this weight on top in simulation. I think in simulation, the range is up till 2 to 6 kg or something. And we are testing already out of the domain in training simulation. And so this is a very hard fall. I don't know if you could hear it. And if you notice, the policy did work for the first couple of seconds, but then since the adaptation module was not adapting online continuously, it failed to generalize. Here is one more result. So it can easily walk on mattress, but without adaptation, it fails to generalize and kind of falls after a few steps. Let us also analyze this adaptation module in more detail. So
Deepak,
here,
do you mind if I ask another question?
Yeah, okay.
Jeff here again. So I want to make sure, I apologize if I'm slow in the uptake. I'm trying to make sure I understand. Is the idea that there's no weights changing during adaptation, that you're using adaptation to reflect the fact that the encoder, which is a function of historic, like recent data, will adapt the Z code to try to basically predict what is the Z code of the current world that I'm in. And with that different Z code, then the policy adapts to that world, but where there's no actual learning, learning is a metaphorical term, but there's no weight changes going on during adaptation. Is that correct?
Correct. So, I mean, the way this encoding goes to the network, it's a dot product. So whether you can think of Z as weight, you can think of Z as input. So Z is changing. So it's an input. So the base policy is not changing. Yes, you're right.
And the vector that transforms the data, historical data, into the Z vector, those weights are not changing, but Z itself is changing.
Correct.
In some sense, this is like, you could make the analogy that this is a little bit like the Rubik's Cube work from OpenAI, but where that network figured out how to internally within the recurrent neural network update its assessment of Z. Here you've kind of factored out a little bit more manually.
Correct. You could, so since the base policy had no state, so you can think of it as that in that sense. But one difference from the, one difference from that, when you directly train an LSTM policy, in a way, it's not as clearly disentangled. You're also asking the policy to be robust or invariant to all the changes in randomization. But here you are not asking the policy to be robust or invariant. You are actually asking it explicitly to condition on the changes. So it's like a similar difference between robust control and adaptive control.
Yeah, I would argue the fact that the OpenAI policy that you could have with a linear probe infer the state of the world from the hidden activations implied that it found value in determining those hidden value activations. Like if it was truly invariant, it wouldn't have needed to calculate them. It would have just been robust, but it was kind of doing experiments, figuring out what the Z vector was, presumably because then it conditioned on that Z vector. So my guess is something similar is happening inside that big complicated network. And maybe it's figured out a similar approach, but this is like, totally, this is nice because you can lay it out and like analyze it and optimize it separately.
Yeah.
Anyway, I was just trying to understand the method, but I think it's really cool. There's cool parallels between the two, I think.
Yeah, you're right.
I love the idea.
But so there is one other reason for doing this in our case, actually, one other practical reason. The robot that I'm showing results on actually is a very cheap robot. This robot is $8,000. And I think if you don't want access to the API, it's just $2,000 or $2,700. So it's very cheap. But the problem with that is the motors are not repeatable and they change behavior over time. And biggest problem is that there is almost no onboard compute. And whatever I'm showing is running onboard. So they only have a CPU on board, very small CPU, and that's it. But this decoupling of phase 1 and phase 2 actually helps us make this asynchronous, right? So the faster parts can, like reactive parts can run at very high frequency, like 100 Hertz or 500 Hertz. And the slower part, like processing history, can run at very low frequency, and there is no problem in that. So that's another reason. But if we had like an LSTM or something like that, then you have to process the history at 100 Hertz, which is not possible. I mean, not possible as in the current. It's very hard.
Sorry, so I have a question. I have a question. So what kind of network are you using to process the history that doesn't allow it to run faster?
So we use temporal convolutions, which is I think standard practice. So we could have used recurrent network, but I think since the history is only 50 states and half a second, so we just use temporal convolution.
Thank you.
All right. So let us analyze this module. So I'm running a bit behind my schedule, so let me go a bit faster. So here we ran out of like more complex environment. So this is one of my favorite example. We created this environment where we are putting first oil in the environment. So you can see the person really puts oil it up for the robot to slip. And Ashish is using olive oil for some reason, could have used other cheap oil. And then we also put plastic on the leg of the robot. So you can see this plastic wrapped, but it really slips on this. And you can see it is almost slipping, but it can actually move forward. So let's see it in slow motion. So even though it is almost slipping, it has learned to not fall. I think that is kind of, I really like this result. And here is to initial like Jeff's question about what is Z encoding in the latent space. So here, what we found that the Z encoding or this extrinsic encoding is not encoding the parameters explicitly, but it is encoding like some basis of them. So in the oily surface, this is 8 dimension, we are visualizing 2 dimensional objects, Z1 and Z5. And you can see as the robot walks, these they change behavior. So it is indeed that these parameter values are changing as the robot is adapting, and that helps it adapt to new scenarios. So this is one last example here, where we are throwing the 5 kg weight on the robot while it is walking. And note that this was never shown in simulation, like this throwing behavior. And 5 kg is kind of large weight. So I did this experiment with my students at lab. While they're walking, I didn't tell them that it's 5 kg. I just threw it at them, and then they were actually quite surprised how hard it is to catch while walking. And here it is in slow motion. So notice how the robot bends down when the weight comes on top. And again, this behavior is in a way I would say emergent, because this throwing thing is happening at test time, and the fact of not falling has led this to happen. So here we are visualizing some other values like Z2 and Z7, and you can see the change in their behavior as you throw it. So they both are similar in the beginning, and as you throw the weight, one becomes high, one becomes low. Okay. So now quickly to summarize that this work is kind of at least I think Jeff mentioned the hand work, that is definitely one of the work. But even in locomotion community, there's a lot of work done over the years. For instance, I don't know, like work in control locomotion, learning for locomotion, also sim to real for locomotion from this lab, and from adaptation, meta learning, and all that. So what we did, we compared this method to different types of approaches, like domain randomization, where your idea is to be robust across all the environment, and invariant to system identification, where what if you don't have Z vector and you estimate the exact friction and all those values at test time. And also other methods that adapt in test time, but they take more samples, like 3 to 5 minutes of data. This is like Jason Peng's work, for instance. And it turns out that this RMA works much better compared to all of these approaches. And we did the testing not only in simulation, but also in real world very thoroughly. And I would like to emphasize that the testing was done in real world, and to an extent that the robot broke multiple times while testing the baselines. But this is what I'm a big proponent of, as in we should be doing full thorough testing in the real world and not just in simulation. So in the context of all this prior work, what is exciting about RMA? I think the most exciting thing personally for me are these 3 points. Like, one is this adaptation happening in online without having any hand-coded or heuristic control stack at the bottom. So we are not assuming any leg predefined trajectories or motions. Then it can generalize to new terrains with limited training. And then this asynchronous design, this 2-phase design, which allows us to run this on low compute scenarios. But focusing on the first point here, so just underscore
question. Okay. So yeah, it's also about the first point. So why do you think a hand-coded heuristic will it be harmful to your task if you use a hand-coded heuristic, or why is it beneficial to not use a hand-coded?
I just come to it in the couple of, I think discussion will be answered automatically.
Okay, thank you.
Okay. So here, since the robot is blind and it does not have any foot patterns, like any pre-hand-coded thing, it has learned this behavior of like avoiding obstacles by slowly moving the leg upward. So as we see here, so this is one of the benefits of not hand coding. Like if you look at it in slow motion, the robot actually has learned this behavior that slowly move it upward while you avoid the obstacle. And we found that this behavior is very consistent across environment. So here is one more one. Okay.
I have a follow-up question on that. So I'm not sure if you're aware of the ETH Zurich's work that's similar. So they are using a I believe they're using a predefined sine wave for the leg, and they can deal with this scenario pretty good. So I don't see why that would be a problem.
Oh, so I think in their case, the robot is actually very high. So it's a big robot. And if you notice all the videos, by the way, that work is great. I'm really a huge fan of the work. So nothing bad about the work. I have only good things to say. But still the point of this, they can avoid this because they're very high clearance. And when you have very high clearance, your gates are really energy efficient. For instance, look at this example here that I showed earlier. What was this example? Like this example here. So on the top. So if you see, I can play the video. Like this kind of weight, if you have high clearance, if the obstacle is not that high, then we have no problem in doing that. But if you have an obstacle which is higher than this, then what will you do? Like there is only a limit until which you can avoid the obstacles, right? So in their case, I think the obstacles that they show are mostly where the clearance kind of takes care of it automatically. Anyway, the right problem here, the right approach to do this is neither of this, neither there nor ours. I think the right approach is to have vision and avoid the obstacles intentionally rather than via these heuristic mechanisms. But the bigger reason for us not hand coding thing is not really all of these practical reasons, it's more of a philosophical one. And what we were really inspired by is this work on the side of studying locomotion in babies. So for instance, there is this work from Karen Adolph. And I don't know if you guys know Karen Adolph, she's a professor at NYU, and she studies locomotion in babies. And she's like a world authority on motor development in kids. And she's also the student of Eleanor Gibson, who did this famous visual cliff experiment with babies, and also the wife of J.J. Gibson, who's a huge authority in computer vision. Now, one of the papers that I really like from Karen Adolph is this work on like studying locomotion in kids, where she kind of argues that kids the locomotion pattern in kids do not fall into this predefined notion of gaits or leg primitives or leg motion, while in kids the locomotion is more general, and there is no stage in the development of kids where these regular patterns are there, which is a surprising result because this is kind of face-to-face countering 100 years of work in biomechanics, where people have completely focused on gaits. And also we kind of know that this is not completely true, because in animals, we have seen very structured gaits, like walking, amble, pacing, trot, etc. And this has been studied very well in horses, where these gaits emerge. So there is kind of a mismatch, like both of them are natural behaviors. In babies, we don't see those gaits in complex environment, but in horses, dogs, cats, elephants, we see these gaits. So how do we reconcile both of these stories from a scientific point of view under the same framework? Now, one point to note that these animals, whenever these gaits have been studied, they have been studied in the context of flat terrain, where these gaits are structured, while argument from Karen Adolph is about uneven and complex terrains, where the gaits are unstructured. And we would like to do is reconcile them in the same framework. And one way to do that is to basically hard code the gait. So if you hard code the gait, as someone asked a question, or foot patterns, it is very difficult to maybe like reconcile this story. Like, how do you get unstructured behavior in uneven terrains, right? So here, before we reconcile the framework, let us take a step back and think, why do these animals have these gaits at the first place? Like, what is it about them that makes them show such structured patterns? And this problem has been studied by lots and lots of papers in biomechanics over the years. And this area has been like 100 years old. And one hypothesis, which I personally like the most, is this hypothesis of energy, which was argued by this paper on the top left, 1981 paper from Hoyt and Taylor. And their argument is that it could be the case that the animals have evolved to conserve energy. And that's why they show these regular foot patterns that we see in them. So for instance, they made this plot here in 80s. So y-axis of this plot is showing how much energy is consumed by the horse. The way they measure is by measuring oxygen level that they consume. X-axis is the speed of the horse. So as you can see, as the speed increases, different gaits happen like walking, trotting, gallop, canter. But the key argument is that if you try to walk at high speeds, it's very inefficient. If you try to gallop or trot at low speed, it's very inefficient. So it's like a bell curve. And you find the right gait at the right speed, which consume by this energy hypothesis. And we thought, okay, maybe this is one way to kind of bridge the gap between these two questions, like structured gait patterns and unstructured gait patterns, and see what we can come up with. So what we did is very simple idea. We take the same framework as RMA, and we additionally minimize energy on top. And surprisingly, what we found that if we minimize the energy, in addition to moving forward, just two terms, energy and moving forward, we found that different gaits emerge at different speeds. So for instance, at low speed, it walks, at high speed, it trots, and it's at highest speed, it bounces. Okay, so it's the same scenario. But in the first example, we are training on a simpler terrain. So note that this terrain is not as complex as the earlier one. So it's almost flat with some bounces. And here are examples of the gaits that have emerged completely. So note that now if you see the gait pattern here, it is not unstructured like RMA I showed before. It's actually very regular walking pattern. But these gaits have emerged here and not hard-coded. Now, if you take the same algorithm and you change the speed, same thing, no change, just change the speed, the gait is different. So now it's trotting, where the hind legs track the front legs. Again, if you change the speed to even higher, it starts bouncing and galloping forward. Now notice that one can hard code these gaits for different speeds manually, but that's not the goal here. Right? The goal here is something that automatically changes gaits as you change the speed and is emerged from scratch. And I hope that this kind of answers the question that was asked about pre-programmed gaits. One interesting that we found here is that the flight phase has emerged in this robot. So if you see this robot, it's completely in the air. And this is something which I found out later that controls people really appreciate, like this gait of all being in the air, because it's kind of very hard to get, like where you have all feet in the air. And here's a quick illustration. So at low speed, it walks. And here we are showing the classical way of showing gaits, like foot patterns in a graph laid out in a 1D series. At trotting, it's a different gait. So let me skip this in the interest of time.
Just a quick question, if you don't mind. So what energy metric are you using here? Because there's a variety of different energy metrics.
I think we are using work.
There's true mechanical work. There's positive mechanical work and negative mechanical work. And
it's mechanical.
Have a field day with all this stuff. So yeah.
Yeah. So we did the simplest thing we could implement here. So we did positive mechanical work. So we just minimize the mechanical work done by the robot. So it is not counting the electrical compute the robot is using, which I think is what biomechanics prefer, or they call it energy, like I don't know, transport energy or dimensionless energy term.
Yeah.
Optimal.
So the negative mechanical work, like that counts against the energy objective, or that counts as energy stored that you can then use again. And
so we are basically computing, I think the dot product of torque and the angular velocity. So you minimize that for all the joints. Yeah. So
okay, but and that's integrated. So that can be negative. So in principle, you can store that energy somewhere. And
yeah,
that's the drawback in some sense of using pure mechanical work. If your actual actuation can't store that energy, but
But I think these motors cannot really store it. So they're like
right. Yeah, exactly. Yeah.
Yeah. So
okay. And I was just wondering.
Yeah. So in this, maybe you're right. Actually, maybe in this framework, it amounts to the same thing, but not in general. And then we also compared. Okay, what this? Can I just finish like a couple of minutes? Yeah, and I'll come back to this. I think I'm running way behind. I might have to skip the second half of the talk, but it's fine. So we'll just do one thing very well. Okay. So here, then we also compared this robot. Okay. is like, so we found this analysis in biomechanics, like this is called Froude number analysis, where they assign a scalar metric depending on the gait of the robot and the shape and the dynamics, etc. And with that robot, we found that our robot is actually not a dog, which everyone calls it like a robot dog. It's actually a sheep and a horse by this analysis. So across all the gaits, the Froude number turned out to be in the range of horses. And that's why, so we decided to make the same plot as this Hoyt and Taylor. Oh, sorry. Here on the left is the plot for our robot, where I just skip it, but the key idea is the same. Like, we found the lowest energy configuration, and the gait switches from walking, trotting, and bouncing because depending on the speed, and which is the same trend as in horses, like walk, trot, and gallop. But note that these plots are not exactly comparable because the y-axis is work here, and over there is oxygen. So it's not completely same. You have to take into account the electrical energy as well, which we did not found it hard to compute. So it's we are working on that. Okay. Here are some of the examples of these gaits. So here we see a robot trotting through this scenario and move forward. We also did the same testing as I did before, but at this time I had moved from Berkeley to CMU, so we did not have the same weights, etc. So we became creative, and we put filled water bottles on the robot, taped onto it to have this payload on the top. And the gaits are kind of consistent and robust to all these variations. Here is one more trotting through the bushes, one more like bouncing through this. Now this is actually very high speed, so the robot kind of goes away very quickly. So the student has to really jump around with the robot. And here the student is pulling the robot on the sideways and also pulling it upward. So if we see here, even when you pull it sideways, it's almost tilted. It can maintain the gait at such a high speed. And then similarly for pulling upward as well. Now, if we repeat the same experiment on the complex terrain, like here, like in this case, and it is also argued by other papers in animal locomotion as well, that in complex gaits, the horses, dogs, sheep, they do not display structured gaits. They only display structured gaits on flat terrains. And here we do the same thing. And when we do the energy consumption in complex terrain, no matter what the speed is, the gait is always unstructured and does not fall into those categories. Like in this terrain or in here. Now, if you see the plot at the bottom, the gait is not structured at all, which is kind of consistent with the story that Karen et al. Argues for babies. And this was the part one, which I think took way long for me to finish. So now maybe I have a question here, like, should we go with the part two, which I think is much shorter, or should we just focus on this and have this be understood in more detail? What do people want?
Let's see. Yeah. I mean, it's the usual Zoom dilemma. I think there will be people who have hard exits and others who don't. So yeah. And Aaron, as far as the recording goes, does it matter for you?
No, we can go as long as you're available.
Yeah. So yeah, but let's try not to keep it too long, I guess. Yeah. Thanks.
Yeah. Okay. So let me just do it real quick. So this was like same task, diverse environment, and then focus on same environment, diverse task. And I'll go super fast on this, but just to stop me if you are not following something. So before I talk about diverse task in the same environment, let's consider like how do we train agent to solve single task in the same environment. The most common approach is imitation learning, but we all know the drawbacks of imitation learning. Like you have to collect data, tedious for the expert, and this is to be repeated for every new goal that the robot is given. And furthermore, other approaches like learning from reward or cost function like RL, etc., it has the same problem. You have to design the objectives and reward function again and again for every new environment that you would want to do. So if you really want the robot to generalize to diverse number of tasks, it would be most ideal if the robot can discover those tasks on its own, kind of like self-supervised learning, etc. And this is what is the focus of one of our recent work, where the problem setting is we want to discover task at training time and then learn how to solve your own discovered task. And then at test time, the hope is any new task that the user is giving you, you would have discovered that already at training. So you can just do it at test time directly, zero shot. So take unsupervised task solving without any sort of supervision, neither at training nor at test. And this problem of unsupervised exploration has been studied a lot, like including my own work from the past, like curiosity and all that. But the major problem with all those methods is like twofold. One is either you are not able to, either you can explore very well and get the skills. There is no easy way from those unsupervised exploration to actually solving goals at test time. And second, the exploration itself is very limited. And let me show you a demonstration as to why is that the case. Like these are like examples of the, I don't know, like most pervasively used methods in exploration, like goal generation, and self-play, counts, curiosity, and all this. But in most of these scenarios, whenever you generate a goal or whenever you explore something by a prediction error or something else, it is almost always ends up being the case that you are exploring near the frontier. So you sample a goal which you have previously visited, like it may be at the boundary of things that you have seen, or this can be an area where your error is high, and you go and explore those things further. And by doing that, your area, the frontier, explores. But if you really want the robot to discover thousands of tasks in its environment, which is complex, you want to explore in a much more efficient manner, in a way that can explore beyond the frontier. So the goals that you generate for yourself has to be really far away from the thing that you have seen. But it is very difficult to imagine scenarios that you have never encountered. And the question that we focus here is, can we sidestep this problem somehow? Can we somehow explore beyond the frontier and discover huge variety of goals without having to generate one from your training set? And here the idea is really simple. The idea goes as follows. So we build a world model of the environment. So the agent explores, collects some data, and then builds a model. Now from that model, agent imagines a trajectory. Okay, so it imagines a trajectory. Okay, if I do this action, that action, that action, that action, what will happen next? And then it tries to find out the trajectories as to how much uncertain the agent is about the outcome of those trajectories in imagination. Okay, so let's say this trajectory over here, if the trajectory lies inside your frontier, you would already know what is happening inside the frontier. So your certainty about that trajectory will be very high, or you'll be very, very less uncertain about that trajectory. So you will discard those trajectories because you want to pick the one which are most uncertain about. And if you sample more trajectories in here, you can actually, if you find a trajectory in imagination that you are very uncertain about, it is very likely that it is beyond the frontier, because if it was within the frontier, you would not be uncertain. Okay, so this is the basic idea. So you sample trajectories where you are uncertain about the outcome. You don't have to predict what the outcome is. All you have to say is that I cannot predict it. And then you execute those trajectories in the real world. And when you execute that, you execute this, and while doing this, your frontier will expand because you will execute around this. Then you go back and take goals from this trajectory. Okay, so you discover goals from this trajectory, and then you try to reach those goals directly. It's a directed exploration. And in this case, what really ends up happening is that you end up expanding your frontier very quickly. So think of it this way: you are doing hindsight experience replay kind of thing, but in imagination, which is forward-looking. So you're not just doing it in hindsight, you are doing it in foresight. So we call it prospective exploration. And then once you are done with this procedure, you have learned this policy which can explore. You can also this policy which can achieve goals. And then you at test time, this just reduces to finding new goals with new images. So let me quickly show you some results here. So here is this complex environment where this is again all torque joint angle control. So this is no primitives, etc. So you have to this is a hard problem in this environment to do anything like move kettle, open microwave. And here is a demonstration of the exploration trajectory. So here robot goes and opens the cabinets completely on its own. It opens microwave and things like that, opens the light, moves kettle and all that. So it discovers many goals during training. Then at test time, you can have the agent perform different tasks, and you can give it diverse amount of goals. So for instance, here the nice part here is that we train a single policy only once, but at test time, we give it lots and lots of goals to achieve. We can ask it to make shapes with the body, organize the blocks, or open cabinets, or do the things. So let's see one example of this task here. So this is the initial image, and we show this robot this goal image. And in this image, the cabinet is open, the light is on, and the kettle is moved. Note, the robot has never been supervised, neither at training nor at testing. And it sees this image, and from its own image, it tries to match its current image to this goal image. So in doing that, it moves the kettle, it turns on the light, and then it opens the cabinet. And this is completely zero shot. So it is able to, and this is like thousands of actions to be done in the sequence to figure this out. And okay, it can also work in more environment. Again, this is
Can I just ask a quick question on that? So if you have like a cabinet with a small handle and you have no idea what that a handle is an affordance, then it's going to take a lot of random motion of the robot, like years, presumably, before you discover that if you put the gripper through the handle and then you pull, that it opens. So aren't some of these things like a little bit too much, like looking for a needle in a haystack, or
I totally agree. So think of the way I think of this work is it's going beyond the current exploration methods, including my own previous ones, in able to discover goals in these complex environment. Like for instance, I have not seen a result in this kitchen environment. So it's actually a complex environment in some ways. So I've not seen a result in this environment which does not use demonstration or does not use very shaped reward functions. This environment is already hard with shaped reward functions. And demonstrations with that you can solve here. So I don't know what the limit is. I know that this approach is not there. It can discover, if you have a very complex environment, it's exactly like discovering needle in a haystack. So it might not generalize, but we are still trying to figure out the limit of this approach as to how far can it go. But
I bet you Go Explore. I bet you Go Explore could solve that problem. All those needles in a haystack, because it's so efficient in phase one. It doesn't have to learn to do it reliably. You can do it deterministically. And so you could set a goal with this method, including the hard example that Michael just mentioned, and then run Go Explore to find the solution trajectory, and then use that, then robustify that into the policy, and then repeat the process.
So your suggestion is that discover the goals using this prospective business, but then try to achieve them using Go Explore. Correct?
That's right.
So like a merger of both of these approaches. Yeah.
That's right.
Yeah. So yeah, actually this could be efficient. So currently the way we approach or reach the goals is kind of very simple. Like we just condition on them and then just go there. But this could be a
which, if you've done a good job of proposing a hard challenge, then gives you a hard exploration challenge in front of you. And correct. Go Explore is very good at solving that part of the problem.
Yeah. Although one question is like, is it easy to do without relying on like the reset mechanism? But we can also discuss that offline.
You can use the reset mechanism in the simulator because you have a simulator.
Correct. So you can use you can use it in the simulator. But like one of the setup that we are trying right now is to do the exact same setup in real world.
So then you do all this in simulation, and then you'd have to like zero shot. You'd have to cross the reality gap. Yeah, you wouldn't want to do. You couldn't do. Well, actually, you could do resets, not perfect resets, but decent resets in the real world if you just knew like the state of the arm. But then you've got a little bit of stochasticity you'd have to handle.
Correct. Yeah, I think I kind of agree with you, like that there is a lot of possibility in improving this. However, like I would like to point out that the main insight here, which perhaps for me is that this like completely sidestepping the problem of, which I think is also in Go Explore in some extent, that you should not generate goals, you should kind of discover them from the environment. And here the whole thing is model based, so it can actually imagine far away goals or trajectories. So it's easier to find the trajectories than it is find generate goals. I think that's the main insight. And
I love that idea. One question I have: how do you do the uncertainty estimation to pick the goals?
So we had a paper called disagreement based exploration. So it's that kind of follow up to curiosity. So curiosity requires prediction error, which requires ground truth. but we do disagreement. So we just maintain like a bunch of models, like 5 or 6 models, and they predict the outcome. And if they all disagree from each other, we say that the agent is uncertain. Okay, yeah. So very simple. But the nice part is of disagreement is this completely differentiable, by the way, because this is just variance. It does not, it's unlike curiosity, it's completely differentiable.
Would that handle stochasticity inherent in the world?
Correct. Yeah, it does, because each of the models are themselves deterministic. So they only capture epistemic uncertainty and not aleatoric. So this handles the noisy TV scenario, for instance, with remote or something.
If there was like a slot machine in the world.
Can I just at some point, I don't know, I do need to just try to keep, like, it sounds like these are great points for discussion, and maybe Deepak can hang on at the end.
Yeah, I can.
But we should be fair to the audience and let people wrap up their,
yeah. Okay. So I think these are very good questions. I think so. But let me just. So here is like a result of robot trying to make the shapes at test time directly without any supervision. And finally, one I just mentioned quickly that we also train a single policy across all these environments. Since it's completely unsupervised, you don't really need to worry about like objective clashes and multitask thing. So this is all trained, and we can solve many of these across environments. Finally, this is the end of the talk. Almost like talked about this learning from same task, diverse environment. We talk about adaptation piece here, and here talked about goal discovery phase. And we kind of need interaction between these two problems to reach this long-term goal. But that being said, that is not enough. We need many other things like inductive biases from control. So far I was emphasizing that the robot is not using any control abstraction, etc. But I don't mean to say that we should not use one. Like one big thing is like this robot today are kind of quasi-static, as in they can take forever to act at each step, while the real world is dynamic, and controls has a lot of work in trying to model dynamic tasks. So we are also trying to in parallel, trying to integrate the control approaches inside the deep network. In particular, the famous work on DMPs, which are very popular, and we put them inside a deep network and learn end to end. So here's one example where the control can make the difference of night and day. So the robot is writing from the images on the whiteboard. On the left is a deep learning method. It can solve the task, but it looks like a 2-year-old drawing something. On the right, if you use this simple 4 lines of code inside the deep network, the network learns to write very smoothly on the whiteboard. And there are more examples of this. I'll just skip them here. And you also need reasoning, etc. in theory imagination. And we are also working on this. So again, as I promised in the beginning, this talk is not a high level talk showing 10 of the papers. I wanted to focus on one thing really in detail. And here is a quick acknowledgement for all of these work. The first is Ashish and Zipeng, then Russell and Oleg for the goal discovery. And the control part I showed very briefly is from Shikhar. With that, I'll just end here and say thank you to everyone.
Okay, great. Thank you. Yeah. So let's see some real applause and some virtual applause here. Great. Yeah. So let's see. Let's throw it over to the audience for some additional questions.
Yeah, I have a question about learning with just energy consumption. So my experience is that if with such simple reward function, it's really hard to get some really lateral motion. That's why people in ETH Zurich, they design some super complicated reward function for their robots, etc. So I just wonder, what do you have any kind of trick to just use some such simple reward function, or it just work?
Yeah, I think there is not much trick here. So we just have one parameter, which is the weight of moving forward and energy. So we just tune that one parameter. And I think actually one difference is that since we don't assume these predefined like motions, you are giving the optimizer more freedom to find a solution. Because they're joint angle, right? So it's not restricted at all. So maybe that's why it is helping. But if you assume strict like motions, like in the ETH work and do energy, I don't know what will happen.
No, so what I'm saying is, since you didn't predefine anything and your reward function is so simple, so if you look at some of the OpenAI Dream tasks, for example, you can see the motion that they're generating because of the simple reward function that they're using is usually not natural. And like you can see a humanoid doing some crazy arm moving, or the
Yes,
quadrupeds.
yes.
But your motion is so
I think
natural. Yes.
It is because of energy. I mean, if we do not have energy, it's not this nice.
Well, no, but many of the OpenAI gym tasks do have an energy term in there, and so even if you do it to be straight mechanical energy, you get crazy motions out, and so that's why people in the animation community we kind of all turn the OpenAI gym examples into our posters of what not to do, because it produces crazy results, right? So you know, it's not as if coming up with the energy function hasn't been thought of before, right?
Correct. So
first thing that people do.
Yeah.
So
maybe I'm giving a simplistic picture here. So we actually did a very thorough ablation of this as to under what conditions do nice get emerged. So it's not just energy, and you are right. There is actually one other thing, which is the environment. So for instance, if I just do energy and have a flat terrain, the gates that emerge are not that nice.
Okay.
So for like, if you look at this example here, real quick, which I just showed very briefly, this environment, you will see that this is actually not fully flat. Even though like if we want good gates, animal studies showed that we should have a flat terrain, but this is not flat. And the reason that was just mentioned, that if we have fully flat terrain and energy, it still looks like very flailing gate like OpenAI gym. But so this terrain, like some randomization in terrain is kind of useful to make it work.
I see. Okay, thanks.
And other thing could be like, maybe this is quadruped, and I don't know, but there is cheetah also in there, so I don't know. Yeah.
Thanks.
Great. Yeah. So it's the time for, let's see, one more question, maybe. Yeah. Let's see. Jeff or Ben or from the chat. Anyhow.
I'm going to ask one. Is that what you're saying?
Yeah, sure. First come, first serve.
Or Ben, if you want to go. All right. Since Ben's not hot on the unmute button, I'll ask. If there, so you generated these beautiful curves, and actually the horse nature paper generated these beautiful curves. If I understood your method correctly, you request the speed, and then it automatically picks the gait. So then how do you go and fix the gait and vary speed to generate those curves? And also, how do they do that for horses?
Oh, yeah. So I don't know how to do it for horses. So I need to find an answer for that. But I went very fast over this. The way we did this for robot, by the way, I want to still make sure that this plot is not comparable. It is not optimal cost of transport. It is energy. I don't want to get myself in trouble by saying that these plots are comparable. But the way we plotted this, I went very fast over this. So we could not do this from our method, because as soon as we switch the speed, the gate switches to the current one. So we make these plots with MPC based method. So where we force the gate to be this, and then make this plot. So otherwise there is no easy way to do this. And this method is the one from Sangbei Kim from MIT, convex MPC approach.
You just have to find out what they did for the horses and then do it for your robots.
they measured oxygen for the horses. So maybe so need to figure out what is the oxygen equivalent. But I think electrical energy is,
Great. Okay. Yeah. So let's see. I think now is probably a good time to wrap up kind of the official part of the talk. And so and then if Deepak, if you still have a few minutes afterwards, we're happy to post recording. Have some additional questions. So many thanks again. Fantastic. Yeah. Really fun stuff.
Thank you.